is Ana Doblas from University of Massachusetts, Dartmouth. I would like to show you the latest results of a collaboration with Universidad EAFIT at Colombia led by Dr. Trujillo and also my former PhD student, which right now is also a doctor in the same university. So the whole objective of this research is the generation of in-focus quantitative phase images from defocused holograms. So we already know the advantages of holograms. It's just like we don't need to extend the sample, it works for materials and life sciences. We have both amplitude and phase images because we record the complex um, amplitude distribution, and that allow us to generate patterns, kind of like be able to focus computationally at different planes. So this is extremely important for 3D profiling or tracking, as I'm gonna show you in one of the examples. So the whole idea about DHM is about this kind of synergetic behavior with hardware and software, where this hardware is the recording of the interference pattern of a plane reference beam with the light scattered by a microscopic sample. So when the camera records this intensity irradiance distribution of the object, but what the camera records, because it's the intensity distribution, it's a sum of four terms. Where we really are interested in is just the light scattered by the sample and imaged by the conventional microscope that we embedded in one of the arms of the interferometer. So this makes us to have some entangle in the space domain, but if the interference angle between the two reference is bigger enough, we can separate the different terms in the Fourier spectrum, highlighting only selecting the information about the object, and then when we already can separate the object distribution, the spectrum of the object, the idea is just gonna shift it back to the origin spectrum, to the center in the Fourier domain, and then you just go back to your space domain and you can get the absolute value or the phase imaging. So this is well known, this is nothing new here, but it's also well known that the compensation, the shifting back of the object spectrum to the origin, it's a really key part, and it's crucial if you want to have accurate phase imaging. So what that means is that if your sample is thin enough, you know that the background needs to be uniform across, but depending on how you are making the centering, you might have these residual phase values that you're going to observe them as a phase grabbing. So what we did in the past, almost 3 years ago, were like investigating a function, a cost function that we call the total summation metric, that kind of take account how many phase grabbings we have and try to minimize them in such a way that when the function has a minimum, that's where we are calling that is the best reconstructed phase image. So now the problem is we don't have anymore a single image. We have a video where the focus is changed and also the X and the Y. So we need to at the same time provide accurate phase imaging with focusing. So when we are recording out of focus information, so the idea is that our complex information that we are retrieving, after we center the reference, we need to do a back propagation. And usually in most of the regimes that DHM work, this back propagation is using the angular spectrum kernel. So what we really need is to know what is the distance of the object to back propagate the retrieve a complex object. So it's a priori you don't know anything about this distance, right? So what we do is like getting like a loop of a lot of reconstructed images and kind of figure out manually what is the one in focus. but that's something that is a manual process, and it really depends on the experience of the researcher. So a way what we are proposing here is we don't want somebody to go to all the manual reconstructed face images to say which one is the focus. We know that there are these sharpness metrics that they quantify the degree of focusing or focus on an image. So let's try to analyze which one of these metrics provides a minimum on the when the sample is focused, and let's try to minimize them within the platform, the framework what we originally have for the quantitative face imaging. So we cannot show that from all those sharpness metrics, the normalized variance has a really deep minimum value when the sample is focused, and look that when the sample is focused, if your sample is phased, that means that your reconstructed face image needs to be almost transparent, right? So we already identify, it's true that Tamura coefficient and also the teragram variance, they also have minimum values, but if you look like kind of like the slope, the deepness is going to be higher for the normalized variance, so that's why we choose the normalized variance as the metric to minimize it and put in our framework. So a framework is kind of like you just do all the steps until you kind of select the object spectrum. And when you select the object spectrum, you define your function to be normalized. So your synergetic cost function, which is the sum of two terms. One, which is the normalized variance, that's the one responsible to estimate what is the correct distance to reconstruct the in focus image, analyzing the amplitude image, and the other one is the total summation metric. We kind of like choosing the C value and then try in different angles of the reference. You're gonna see how many wrappings, or what is the reconstructed face image with the least number of wrapping. So at the end of the day, what we need to get is the angle of the reference and the actual position. And you keep doing this minimizing over a search that is doing the minimization process. So this is kind of like the another way to show up the steps about it. Like the kernel, that's the angular spectrum kernel. This is the one that is going to be useful for the normalized variance. And this is your digital reference wave where you have the parameters of the reference, the Umax and the Vmax, that you need to use for the accurate face imaging. So what we need to show is that we're going to have a minimum value when all of those values going to converge, and that's going to give us the focus sample with the least face distortions. And this is why one of our results, experimental results, where we have red blood cells that we defocus them around 50 microns, and those are the reconstructed face images, and the same results from the epitheliatic cells, where we have this kind of like three-dimensional mappings around. So problems that we have seen about the algorithm, so the method seems really robust, always that we are within the angular spectrum regime. So that means that if we are really out of focusing, like for example this scenario where the diffraction patterns are not really recorded completely within the camera, our method fails, but that's something that is expected. The other thing that we see is that it sometimes depends of your cell density and kind of like your sample. So that's a little more that we need to find why we are sometimes not getting the best results, but overall it's definitely faster than if we do this same process nested for loops. And when we are checking the values, the manual values from the micrometer with estimated ones, they are really close by, showing that we are close and we are not getting any weird estimation about the values. So we wanted to go a step ahead and kind of using like a video, a holographic video. So here what we have are cells, sperm cells that they move across the field of view. It's hard to see them on the holograms because they are almost transparent, But here are like the face images. So this is like the different cells that were clearly, they were moving in 3D, so they are out of focus, and this is like when we are focusing them and the distance that we are getting. So now we know the distance, the centroid distance, x, y, but we also know the c value, so we can really generate this kind of nice 3D tracking across the time of how the position is moving for every sperm within the field of view. So just a summary, we just proposed an automatic method for reconstructing face images with minimum face distortions using autofocus holograms, and we validated doing 3D particle tracking. One of the beautiful, or one of the keys of the algorithm is the minimum requirements. We only need the wavelength and the pixel size, but we don't need anything else, no more input from the user. So the idea of this whole algorithm is the synergetic minimization of two cost functions. One, the normally variance that is help us to estimate the C, and the other one is the total summation metric that is getting through the face image. It gets definitely 20 times faster than if we do this in for loops, and we have been able to implement it not only in a static but also dynamic samples. I just want to highlight that this paper has been recently been published in Optis Letters, and you might be able to see our GitHub with the algorithm to be downloaded and be used for you. Just we want to acknowledge as always our funding and every member of the group that it has helped us to do these results. And please, if you have any questions, don't hesitate to kind of contact me or Carlos and ask us questions about it. Thank you.